Hello, everyone. Hello. Hello, welcome to those of you who've just joined us. Welcome to the final talk of the DSF morning session. I need to be on the right page, excuse me for 1 second. So, in introducing this talk, I think whenever we go to data meetups and see data talks, we always find everyone's keen to say how brilliant they are and how amazing their product is and so on and so on. And it's really actually really rare and really refreshing to hear someone coming to talk about something that didn't go so well. So, with the learning from that, I'd like to talk about, to introduce Cecilia Chen with her talk title, How Not to Run a Consumer-Side Experiment. Cecilia is a seasoned behavioral economist and a senior data scientist at Deliveroo. She's also a senior lecturer in the economics department at the University of Exeter. Her research combines experimental methodology, game theory, and insights from psychology and sociology. That's a lot of ologies.
I know.
And she holds a passion for bringing behavioral science out of academia and into the real world to drive consumer behavior. Can we give a round of applause for Cecilia, please?
Thank you, guys. Is the mic working? All right, cool. All righty. I think now I'm officially the major obstacle between you and the lunch. So I hope the obstacle will be fun, and in the process that you learn something, and hopefully you have something to take home with. Okay? Alrighty, let's get started. So what am I going to talk about today? Right, so I think we're going to talk about how not to run an experiment. So we're going to talk about how to run it, and also I will tell you a story about how not to run it. Okay? All right, so a little bit about me. Thank you for the introduction. So I'm a senior lecturer at the University of Exeter. So what I do is I research and teach behavioral economics and experimental economics. So usually for my day-to-day life, I run a lot of laboratory experiments, field experiments, and online experiments. Okay? So for those of you guys who are not familiar with people taking subjects into the laboratory and run experiments on them, maybe this is what you think an experiment the economics look like, right? This one? Or maybe something like this, because we have to put a little bit of money into the economist view, right? How much money are you willing to pay to save a mice life? But actually, this is not a joke. This is a real study. And the mice will die if you don't pay for it. Okay? So this is a very interesting study, but we can talk about it later on if you're interested. So usually what actually happens is a bit more mundane than what you imagine. So when we run experiments with subjects, we invite them, especially if you're running laboratory experiments, we kind of invite them to laboratories, and usually they're making decisions independently in their own kind of compartments, and usually over a computer. Okay? So it's not as that cool. All right, so, and also I want to highlight that experiments, they're kind of, I think the more familiar term that we have is A/B testing. So essentially, A/B testing is actually kind of experiments. In A/B testing, you have the control and treatment, but in usual experiments, there are more kind of variants that we're testing simultaneously. So essentially, those are the same things. All right, so what am I going to do today? Right, so today, like I said, I want to kind of tell you a little bit about a particular type of experiments, in particular experiments with imperfect compliance. And I will also tell you a story or an example in terms of how I apply those tips from the learnings to a real kind of experiments that we ran and what my mess-ups are, okay? And at the end, hopefully, you'll feel comfortable and okay making mistakes along the way. All right, so what are those experiments with incomplete compliance? So usually on the left here are the usual type of A/B testing that we're all very familiar with, right? So we know that when you have a feature, you usually want to test it against the current version, and what you do is you randomly assign some units into your control conditions. So those are going to be the existing version that your users or units of test are experiencing. We also know that you're going to randomly assign the others to the treatment condition where they can experience the new feature. Okay? So as you can see, that's a kind of a more common form of experiments that we all kind of are familiar with. But there are a lot of occasions, a different type of experiments where there are potentially non-compliance. So you still have your units allocated randomly to the control, but for those units that are allocated to the treatment, they're not necessarily all treated. So this is a scenario where we call the experiment with non-compliance. So what do I mean? So give you a couple of examples to kind of help you get the concept, to understand the concept. Think about a clinical trial, right? So when you run the clinical trials, you need to have a randomized control trials. You have some of the patients who would be allocated into the placebo, and you have some people who are allocated to the actual drug, okay? So when you have those people into the actual drug, sometimes they may or may not actually take the drug, okay? So either they forget, or there are various reasons that they fail to take the drug. So that's the case where there are some incompliance or non-compliance going on. So another example, probably a bit more relatable. So think about there might be some sort of health regimen, right? So a particular agency is thinking about, hey, we want to test whether a particular health regimen is going to help treat a particular type of disease. So those patients who are allocated to the treatment conditions are given instructions, things to eat, time to exercise, steps that you have to achieve every single day. Then think about for yourself, right? Are you going to seriously follow this regimen, religiously? Probably not. And that's another kind of example in the cases where even if you're allocated into the treatment conditions, you're not necessarily treated. The more concrete example that are relevant to what we do is think about a feature A/B test, right? So you might release a new feature, a new experience, a new journey for your users. But when you're doing your testing, it's not necessarily the case that all your users that are allocated to the treatment are actually treated or they're actually using the feature. So coming back, so that's kind of a typical example of you have your subjects in the control, you have your subjects in the treatment, but not all of them are actually using your feature or experiencing your feature, okay? So in these cases, what people normally do is that we're gonna calculate the average treatment effect. And that's what we usually do. We're gonna look at all the outcomes or the metrics that we really cared about. We calculate the average, and we subtract the average of the control of the key metrics that you care about, and then we call it a day. The problem is when not all of your units are actually treated, what you're calculating is not necessarily the average treatment effects. It's actually what we call the intent to treat effect, right? So all those other guys, look at here, they didn't really experience your feature, so they're not really treated. So when you're calculating using the subtraction of the mean between the treatment and control, you're not really understanding what is the impact of your feature, what is the improvement that your feature is bringing to your company. So you can do that, but I would like to highlight that you may not necessarily want to calculate your average treatment effect or calculate the intent to treat. The reason is, remember at the end of the day, as a data scientist, when you run your experiments, you need to make recommendations. You want to tell the business stakeholders that your feature that your engineers work so hard to release is actually making a difference, right? So, and we want to help our engineers to show that their work is making an impact. And our analysis is essentially the way to achieve that. But in that particular scenario, if you calculate your average treatment effect by lumping up all those guys in the treatment and compare that with all those guys in the control, then you're actually not doing any of your engineers any good. The reason is that when you calculate the simple average treatment effect or intent to treat effect, you essentially is diluting the impact of your feature. Well, the reason is, if you look at those guys, right, they're not really experiencing your feature, and putting them into your sample, you are essentially diluting the real impact of what your feature could have had. So that's not good. You have a smaller effect size. And second, when you're doing your calculations, you're putting all those guys into your sample as well. And you know they have variance, right? So things change around. When you do the comparisons, you will notice that you would also have a lot bigger variance. So now, when you have an effect size that's diluted, that's a lot smaller, and you have a variance that's a lot bigger, that means that your p-value is going to be a lot bigger, and it's a lot harder for you to achieve statistical significance. And that is what I want to argue, things that you don't want to do. So what should we do instead then? Well, so there are a couple of solutions. Some of the solutions are a bit more elegant in a way than others. But some of the solutions are probably a bit more universal than others as well. So the first solution is you can actually solve this analytically. So what do I mean? The intuition is you can still calculate the average treatment effect, but you want to pump it up by dividing your actual average treatment effect by the percentage of your subjects that are actually treated. So essentially we're saying, well, we calculated a diluted average treatment effect, but we recognize that we're actually only calculating the effect based on the limited sample. So we really need to pump up the effect size by dividing of the percentage of people who are actually treated. This way, you will drastically bump up your treatment effect, and that becomes what we call the local average treatment effect. So that's kind of intuition analytically what you can do by taking into account of the percentage of people who are actually treated. So this one basically gives you a point estimate. But if you want to go the whole shebang, a more kind of appropriate way is actually you use a kind of IV instrument. So the actual treatment status, you will use that as an instrument to calculate the actual effect size for when you have only limited units who are treated. Okay, so we're not going to go to this stuff. This kind of, you can download a couple of packages and use the IV reg. So what I want to talk about is there's another way to kind of go around this problem. So you can do it in an analytic way, thinking about how do you, given the data that you have, how do you process it? Another way is actually thinking before you run analysis, how can you design your experiments such that you're already taking this problem into consideration? So what do you want to do if you have a potentially not everyone's actually been treated? What you want to do is, in this scenario, design an experiment such that even within the control conditions, you would have some subjects you can identify that those are the ones, should they be put into the treatment conditions, they would have been treated. So that's creating a counterfactual in the control condition. So once you're able to identify those guys who are in your control, but they could have been in the treatment, then the next step, you can simply drop all those guys, both from your control and your treatment, and only focusing on those guys in the control who are identified as they could have been treated with those guys who are actually treated. So this way you can see it's a bit more elegant in the way that your analysis is extremely simple. So it's as simple as let's compare the averages in the treated versus the untreated or counterfactual. So the same average treatment effect mechanism or the step that you would follow. Okay? So that's the two ways that when you face a situation where your feature doesn't have 100% take up, what you can do. The next thing I want to do is tell you a kind of an example in terms of how I used the experiments to solve the problem of incomplete compliance and how I kind of stumbled things through. Hopefully you learned something from that. All right, so when I joined Deliveroo, so essentially I was advertising to my team that I've done years and years experiments. I'm really the expert that you should listen to when running experiments. Okay, so that's kind of the impression I want to set into them. And then 1 month in, we have this problem that essentially there are times that some of our restaurant partners, they would give you a delivery time promise that's way too ambitious. And so the problem comes in that those partners, they usually set a fixed delivery time. For a lot of cases, if you live too far away from the particular restaurant, the time that's set by the restaurants are not necessarily realistic. And this problem becomes particularly urgent when our fierce leader kind of talked about it in a company kind of workplace and highlighting this is really a problem and you guys probably need to look into this. So kind of after getting a little bit of push up from the higher execs, we think, okay, really, this is a big problem. We need to jump into action and try to fix it. All right, so what is our solution? So our solution is trying to kind of manage the negative side of the inaccuracy in the promised delivery time. So we kind of implemented an algorithm such that if the time that as a restaurant that you can deliver to a customer that's actually longer than, or actually shorter than the time that we estimate to travel to you, in that case, we're actually going to replace the promised kind of delivery time with the travel time instead. So essentially, in a lot of cases, if the restaurants are too far away from you and they promise 10 minutes delivery time, we're going to replace that time with the actual travel time. So that's our solution. Now, once we have the solution, it's time for the experiment. So this is a scenario that I would like to highlight that it will have imperfect take-ups. The reason is, remember our algorithms, it doesn't modify all delivery times. It only modifies a subset of them. So if you, as a restaurant partner, you're particularly ambitious in saying, I can always deliver to anywhere in London within 5 minutes, then you're more likely to be modified. But if you are a restaurant partner who promise a more reasonable time, then we're not going to modify your delivery time. So from the way that we kind of operate our algorithm, you know that even if you are a user that are allocated to a feature, you're not necessarily going to have actually experienced the feature. If you live very close to a particular restaurant, and that restaurant is really reasonable in setting up the delivery time, then there's no way that our feature would ever be called. As a result, although you're allocated into a feature, you're actually never treated. Okay? So that's what I mean, that this is a good example where we have a situation where when we allocate subjects to a particular condition, you're not necessarily treated. As a matter of fact, a lot of our users are not experiencing this new feature that we're trying to test. So what do? Well, following my own recommendation, I want to resolve this problem from the root by design. So what I did is we run the algorithm for subjects who are both in the control and treatment. Okay? But we're only going to log the data, whether those guys will have a modified delivery time. But when they actually go through their app and the ordering experience, they're not actually going to see the updated delivery time. So that's what I mean by identifying those units that would have been treated should they be allocated to a treatment condition. Okay? So we log them, but we never show them the actual updated delivery time. And on this side, for those units that are actually treated, we know that their delivery time were modified. As a result, this way we identify the counterfactuals that could have been treated but wasn't actually receiving the treatment, and we also know those guys were actually treated. Then in the analysis, you can kick out all those guys, kick out them, and only compare those guys with those guys, and voila, you have your treatment effect. Okay? So this is the plan. I think it works perfectly. So as a data scientist, one of the important things is you need to log your data, and you need to communicate to your engineers to log the data that you need. Right? So I think I told my engineers that we need to identify the counterfactuals, and I made sure that I was able to identify those units that are treated in the control, should they be in the treatment. And I also logged what happened to those users who are actually kind of treated. So I identified all of that. And I decided, OK, looks like the testing data is looking good. I have everything logged. And then we just roll out the experiment. The only thing is, 6 weeks later, I thought I logged everything. I didn't. I didn't log the identifier that would actually link the treatment allocations to the outcome. So I know whether you are in the treatment or control, or whether even when you were in the control, whether you are likely to be treated or not. But I didn't kind of log how can I link those guys to the outcome metric that we really want to measure. Okay? So after 6 months later, when I saw my data and I realized I have 2 piles of data, but I don't know the connection between them. And at that point, it's a little bit embarrassing, to be honest. Coming out saying you're the expert, but in the end, when you do analysis, you realize I can't actually do the analysis because I cannot link those 2 together. So I was struggling and thinking about maybe I should go back to the team and ask them to rerun the whole experiment. But there's some kind of exact pressures. It's not particularly a great idea to ask to rerun. So ultimately, I mean, we come to a kind of a satisfactory end that I was able to try to use a timestamp to link their assignment and the outcome variable. Although it's not a perfect solution because using timestamp to match is not accurate. But hey, I'm not in academia anymore, am I? Come on. So it's, as long as it's good enough, it's satisfactory enough, we should call it a day. So that's what I did. So I didn't ask our engineers to rerun it. Instead, match the data, and it's a good enough level, and we rolled out the features. Turns out the impact is actually quite huge once you're able to kind of isolate those who are actually receiving your conditions. OK, right. So that's the story. What's the takeaway? Log your data. If you don't know, if you know that you need the data, log it. If you're unsure whether you should log the data, log it. If you kind of like, I don't need the data today, log it, please. So that's the first takeaway. Log your data always. And then the second thing is, I think it's actually quite helpful for a lot of us to kind of think through the type of analysis that you would like to run beforehand. So hopefully, if I would have kind of run through the kind of analysis I would like to run, I would have discovered there's a gigantic missing link here, and I would have called out engineers. So I would recommend to don't follow my steps on that. Kind of go through the analysis that you have to do and look for any missing data. OK? So that's that. And thank you very much.
That was really good. Thank you. And remember, everyone, log your data.
Log it.
OK, so if we can just remember that we're not passing the mic around for questions, if you could stick your hand up, and Cecilia will do her best to navigate around the room.
OK, I think that gentleman in the back, please.
You need to shout.
Okay, so do the presentation, right? Thank you very much. So my question is, why you don't run the experiments at the same time period, multiple experiments at the same time, and try to understand the variance? So you can basically estimate the variance, and in the most conservative cases, what's the best, what's the worst variance in terms of your all the sample size. Do that way rather than you have to downsize or upsize your effector group.
So essentially, we're not restricting data. So when we're running experiments, we're actually capturing data not only for those guys, we're also capturing data for all of them as well. It's just once we get the data, when you're running your analysis, we're going to not include the observations from those guys, and we're going to only focus on the observations from those guys. The reason when you include those guys in, yes, you would have a bigger sample size, but you also have a lot bigger variance. So you see the problem here. When you restrict and also those variances or the observations by including those guys, they're not necessarily useful. Especially those guys, because they're not really experiencing the feature, so you wouldn't anticipate their behavior to change. As a result, including them as a treated, you're including a bunch of useless data that creates a lot of variance. So that's why I'm not saying not keeping their data. The data is still there. It's just when you are running your analysis, you can kick those guys out. They're not really contributing to the understanding of the actual impact of your feature. Does that answer the question? Cool, thank you. All right, that gentleman there.
I'm not sure if the question is similar because maybe I misunderstood one step. But in this exact case study, what is the point of dividing control and treatment? Because I can imagine to use the old algorithm as a baseline, the new one as the new one I want to evaluate, and calculate in the same population what is the mean square error against the goal, the actual delivery time.
So you're thinking about, so I should just look in here.
No, I mean, forget about control and treatment, integrating in the same pool and have two different times to evaluate. The baseline, so the one with the old algorithm as it used to be in the app, and the new one with the corrected algorithm. And then for every sample, do the mean square error.
The mean comparison, you mean?
The mean square error, calculate a metric and see which is closer to the actual time that the delivery guy.
I think there's just a little bit of uncertainty. So when you, at least, well, given our particular example, it's actually not clear ex ante who's gonna see the feature. So there's an uncertainty in terms of how many people would actually be treated versus not. Maybe I'm not understanding your question correctly.
Maybe I did not understand exactly because I thought you are showing a time and you want to know if the time, how good is the actual time according to the delivery.
So yeah, so that's the algorithm, right? So those people who are in the treatment, they will actually receive a lot more accurate delivery promise. While those guys, if you're in the control, I know that you would have been receiving the more accurate delivery time, but I'm not showing that to you. So that's the way to identify, to create a counterfactual that I'm not really releasing the feature to those guys. They're still in the control. So they don't experience the new delivery time at all. But it's just at the back end, for me, that I know, should I place you to the treatment, you would have been treated. But those guys, they're not really receiving the treatment. Does that make sense?
Probably because I would have designed this experiment in a completely different way.
Yeah, so we can talk about that later. Cool. Yeah, go for it.
Sorry. I'm an economist as well, so I'm going to ask,
yay.
what was an instrumental variable that you would use to use the two squares?
Yes, so usually you would regress your, so the z would be the whether you're not treated. So you would regress your whether or not you're receiving the treatment here on the whether you're in the treatment condition or not. And then on the second stage, you would regress the outcome variable on the whether or not the outcome of the first stage of the actual treated status. So the actual treated status is the instrument. And then you have your outcome variables, and you have the actual assignment of the treatment and control. So the treated status is correlated with whether or not you're in the treatment, but not correlated with outcome. So that's why it's a perfect instrument. Yeah. Yeah, go for it.
Did you run this for a particular restaurant? Because when you evaluate if people are to be treated or would benefit from treating, you just say, do they live close enough to the one specific restaurant? How do you do many-to-many relationship?
So it's all the restaurants. So not a particular one. The algorithm essentially is calculating for any pairs between the customer and the restaurants, what's the travel time and what is the actual time provided, what's the promise, and whichever one is bigger, we're going to show that one.
So when you choose on the left-hand side those who would benefit from treatment,
Yeah, we don't. Actually, it's only on the cutting down on the delivery promise that's too ambitious. That's not deliverable. So if you promise a time, say, it actually only takes 10 minutes to deliver to you, but the restaurant said, oh, we're going to deliver to you in 20 minutes. In that scenario, we don't modify the delivery promise.
fair. I mean, I'm still trying to say that what if the person never actually buys from that restaurant that you put them in the control zone, you chose some that they would actually never buy from those restaurants, which are too far for them, they would buy from the new one. How would you treat that in that case?
So in the end, what we cared about, so the outcome variable for this particular experiment is how many orders that you receive in the end. So what we're thinking about is that in the control conditions, we're not doing a lot of modifications, while in the treatment conditions, we are improving essentially the delivery promise. So we anticipated potentially when you see the places that promise to be able to deliver to you a lot sooner, we should see an increase in the order volume, and that's what we found as well. But I want to highlight that that's only evident when we were able to identify those guys and compare with those guys. If we were to run the analysis based on taking everyone in the control and compare with that with everyone in the treatment, there's no effect. It's just because there's a lot of noise. So that's why you need to focus on the would have been treated with the actual treated to identify the real impact.
But then those on the left-hand side, there will always be a restaurant far enough for them to be potentially treated, right?
Not necessarily. Well, they're equally likely in both situations. It's a random assignment. So it's equally likely in both situations. It's just when you are in the treated conditions, then you will receive, some of them will receive the treatments. That's the purpose. But then the type of, say you're super far away from the restaurant, the kind of customer and the restaurant pair, they should be equally likely in the control and treatment because it's a random assignment. Yeah, cool. All right. Yeah, please. I don't know whoever went on first. All right, please.
When you actually work on the good of gene and the actual treated, how do you know, obviously you could have many more in either group. So how do you deal with the fact that the actually treated could be fewer than it could have been in the control?
Oh, okay. So you're saying that how do I know I have a kind of like imperfect compliance problem? Is that?
The number of people in the treatment could be much smaller or bigger than it could have been in the control.
It's actually true. Well, it's actually not true. So essentially, the algorithm runs both for the control and treatment. Because we have a random assignment in the control and treatment, the percentage of getting treated is actually comparable in both cases, which is what we found in the data as well. So when you have a perfect assignment, randomizations, you should anticipate it's the same algorithm. If we randomize the sample well, then you should anticipate, so the percentage of people that are potentially treated should be the same as those guys as well. So it is. Okay, cool. Yeah, please.
Yeah. So given that you have designed the experiment to measure time difference between given treatment or not, how valid would it be for to also evaluate the side effects? For example, number of cells on the treated restaurants or similar.
So you're talking about potential kind of a spillover. Is that because of, so there are, yeah, good question. We did answer that as well, good. So essentially, there are two things here. So you know that some of the restaurants in our particular algorithms will receive kind of reduced delivery time essentially, while in the control conditions, it's just business as usual. What we discover is that for those type of restaurants who had their delivery promise kind of reduced, indeed, we kind of observed a very significant increase in their order volume. But what happened is that we did a kind of follow-up analysis. We found is that those kind of or at least in the control, those orders that went to the restaurants that are with a smaller kind of delivery time, it actually is a kind of a substitution. So the total order volume between those two conditions is actually comparable. So what happened is that you have a little bit different cut of pie. So when we have those restaurants who had their delivery time shortened, they have more orders, but at the same time, those other restaurants, what we call our core restaurants, would have a slightly reduction in the order volume. But as a total for a company, the kind of the particular feature didn't really change the total pie that we're getting. So there is spillover, and we were able to identify that. But that is because we were able to identify those guys with those guys. Then you have a lot greater precision. Cool, but good question. Thank you. Yes, I have a gentleman there.
Hi, really good talk. I just wondered about selection effects of when you identify those in control. I mean, obviously in your case, it seems quite straightforward. Your identification method is quite robust. But say you have a propensity model that's not very good, right? So if it's not good in identifying these, you might bias your metrics quite a lot by over-selecting or under-selecting, right? So how did you account for that, or did you check it?
Oh, very good question. Thank you very much. So, so one thing I think I forgot to highlight a little bit is precisely that generally the analytical solutions are a bit more robust. That if you do a corrections, by and large, you would be able to get the real effect. This experimental design solution is elegant, but it's only applied in particular situations. So for our situation, there's no selection into the treatment per se, because it's algorithm. You either receive it or you don't. So it's not because I'm a particular type of user, I choose to be into our treatment. So that's why it's a very good comparison to compare the control and treatment. There's no kind of selection going on. So yeah, this is the caveat for the design is you have to think about your actual problem. What is causing your imperfect compliance? If it's because of self-selection, then you cannot use a design to differentiate it. Unless you, like you said, you can try to run some sort of a propensity score match and try to find those guys that could have been treated in the control, but it kind of defines the whole purpose. You might as well go back to using the analytical solution that just kind of take care of the percentage of people who are actually treated. Yeah, but generally, I personally prefer that, if you can, kind of coming from the background running experiments, I obviously know that there's a lot of fancy methods that are out there for you to identify causalities. But I feel like if you can identify the causality using the experiment at the core, it's a way better solution in ex post kind of analysis, trying to figure out which model can help me kind of detangle the endogeneity. It's kind of, when you're in this business for a long time, you know that depending on the model that you choose, the effect that you have will vary quite a bit. So the analytical solution is always a little bit, not quite trustworthy as if you were doing it kind of the way from the start. You run your experiment, you have the data, you're not changing the data or how you're analyzing the data. If the data is there, there's a method that everyone uses to calculate the treatment effect, and that's it. So that's, I think, is the most robust way for us to actually kind of deal with those type of problems. But thank you very much for your question. I see another gentleman back there.
So at the end, you mentioned that you use sort of a proxy as your output measure because of the log. And I was wondering if then after this, you tested if that proxy was good because you could try an experiment to see if just observed outcomes and you see if the proxy is actually good.
Yeah, good point. Yeah, I know. We could have went back and just rerun it. It was too late to do that. I think our proxy using a timestamp is good enough, and the kind of the outcome when we evaluate this experiment, I think the effect was within our expectation, is making sense. So we kind of made our recommendations to roll out the feature, and that was that. We packed it away. All right, and we see a question here, please. Yeah, this lady here.
Thank you for sharing, but I'd like to know how do you measure or how do you define it's a success?
So when you are running experiments, right, so usually before you even collect your data, you would have some sort of hypothesis in terms of how you anticipate your feature to have impact your business. And depending on where you are, those outcome variables could be as high as the order volume or some other things that potentially are kind of impactful for your particular organization. So you think it through. And before you run an experiment, you probably have to make sure that, should you run your experiment, what should be the metrics that you evaluate against to make a recommendation? So usually those metrics should be something that your organization cared about, right? So even if it's not contributing directly to the revenue, it should contributing, say, to the cost side or user engagement. All of those can be your success metric. The key question is you just have to communicate with the PMs in your team or the more senior stakeholders to see what they want and whether your particular feature can help your team to achieve their goals. Yeah, so just making sure that pick the right ones that actually mattered and run your analysis against those metrics. If you have a significant results, then you can make the recommendation saying, hey, I was able to scientifically, causally identify the impact, and they're statistically significant, so we're very confident about the result, roll it out. Okay? Cool. Thank you for the question. Yep.
I think it's a bit related to what you were just talking about. I think you mentioned that your metric in this case was an increase in the number of deliveries. Is that correct?
Yeah.
Do you know where that comes from? Is it that people canceled less? Is it that there was more confidence because the estimated time seemed a bit more fair, and so people felt more urged to order more? Do you know? Did you do any analytics on that?
Yeah, so the reason that we uncovered is when you have a shorter delivery time, generally that particular restaurant becomes a lot more attractive. Right? Suppose that you're here right now. I think everyone's hungry looking for their lunch. So you probably understand this. If you open the Deliveroo app right now and you are hungry, obviously you're going to pick the restaurant that delivered to you in 10 minutes rather than 30 minutes. Right? So that's the reason why that we think for some of the restaurants, if we can reduce their delivery time, or if we make the delivery time longer, then they're going to reduce the order volume. But if it's shorter, then people are going to make the orders a lot more.
But essentially, you didn't really reduce anyone's delivery time, right? You just increased some of the neighborhood around, right?
Yeah, so they can have received less orders, but then those missed orders come to the other restaurants who can present a shorter delivery time. So that's the spillover that the other gentleman asked about.
Thank you very much.
Cool, thank you for the question. Please.
Have you measured the customer satisfaction
For
better time estimation?
no way.
Did it have any positive impact on the customer satisfaction that would then drive the rating of the restaurant that participated?
We're not sure. We didn't measure that. Because what we cared about is if you are willing to make more orders with us, I guess that's a good sign to say you're happy enough. Otherwise, you wouldn't make orders with us. But yeah, that's something that's interesting capture. But as customer satisfaction, it's hard to measure. How do you measure it? Do I give you a survey? Are you going to fill out that survey? If you don't fill it out, where's my data? Right?
The same person will tend to order more from the same restaurant because they know that this restaurant promises and delivers to what it promises. Because my first idea was when you started describing the experiment was they do not deliver on time, so people are not happy about it. Therefore, they will order less because their expectations are not met. Where it looks now that your experiment was about the distribution of
the orders.
More than the customer satisfaction or their reaction to the food not being delivered on time.
Fair point. We do measure the carrier contacts, though. So we have a measure that we kind of measure how many carrier contacts that you send into the order help to ask where your order is or complain about whether your order is late. I guess that captures, to a degree, the customer satisfaction. So what we found is that with this particular feature, where we're also, when you have a delivery time that's a bit more reasonable, we did see a significant reduction, statistically significant reduction in the carrier contacts that has complaints about the lateness of the order. So I guess that somewhat measures the customer satisfaction. Does that make sense? Cool. Thank you for the question. I think the baby's really hungry. All right. I need to release you guys. And if you have any questions, please come and talk to me. Thank you very much.
Thank you, Cecilia. Thank you.